Today we're looking at the second day of section 4.7 which is arithmetic sequences. So hopefully by the end of this section, again, you can say I can identify and extend patterns and sequences. I can represent sequences using explicit formulas, and I can represent sequences using function notation. So yesterday we looked at this pattern with the fences. Today we're going to use it for a little bit different idea. So if you remember, recursive formulas that we were working with yesterday, given the sequence 7, 10, 13, 16, our first term would be 7, our second term would be 10, which is your first term plus 3, third term is 13, which is the second term plus 3, fourth term is 16, which is your third term plus 3. So again, symbolically stated, here's how we would state our sequence in a recursive formula. Okay, today we're going to look at the other type of formula with sequences, which is called an explicit formula. The benefit of an explicit formula would be that I could pick any term, like I could say the 100th term, and you could find it right away. If we were to use the recursive formula, and I said to find the 100th term, you'd have to first know the 99th term. In order to find the 99th term, you'd have to find the 98th term, and so on forth down the line. So the recursive formula is not very useful if you want to find terms in the future. So what we use instead is called the explicit formula. And the explicit formula is a function rule that relates each term of the sequence with its term number. So there's two different types that you're going to look at today. One type is going to have a sub 1 in it. So again, here's the explicit formula. AN, which stands for any term. To find any term, we need to know the first term, it's saying, and then we need to know the term number and the common difference. So the way I like to look at it is this, which is more like the equations that we've been writing. AN is equal to term 0, which we are going to have to find. It's not given to us in a sequence. And then the term number is our n, and the d is our common difference. So, for instance, for the explicit formula for this sequence, 7, 10, 13, 16, an, any term, can be found by taking this 4 represents term 0, which would have been 4. N times 3, which is the term number times 3, because 3 is our common difference. So another way to write it would be like so. If we wrote it the way the book suggests, we would simply write it like this. AN equals A1, which is the first term, which would be a 7, plus n minus 1 times the common difference, which is 3. So if we were to distribute back the 3 and simplify it, we would come up with the equation that we had written down here as well. Okay, so hopefully this is making a little bit of sense. I'll look at some examples, so hopefully it makes more sense. Okay, so two ways we can write these. First way we're going to look at is the way that we've been kind of thinking through things already, and that would be with a sub 0 or a0. So if we look at this one, recursive formula and explicit formula. So first of all, recursive would have been the one we were working with yesterday, which should have been like this. Always starts out the same way. Any term can be found by taking the previous term. In this case, we're subtracting 4, and A1 is equal to 16. So that's the first way. Okay, this right here was the recursive. Okay, now the explicit, this new type that we're going to look at, I'll give it to you two different ways. So the explicit, first of all, we start out the same idea. Any term can now be found by, in this case, we're going to say, I'll use the A0. So if I wanted to find the A0, we'd have to go back a term which would have taken us to 20. So we'd have a 20 plus, the difference was a negative 4, and the term is n, so it'd be n times negative 4. If you rewrote that just a little bit, you'd have this, 20 minus 4n. So that would be our explicit. If you wrote it the way the book writes it with term 1 instead, you'd be writing it a n is equal to a 16, and then minus 4 times n minus 1. So just a little bit different, ends up being the same thing if you distribute. Either one I would accept. Okay, so let's take a look at this next one, the recursive. And then the explicit here in a little bit. Okay, so the recursive. I'll write it the other way this time. I'll start with my first term. My first term is negative 8. Any term after that, how do you find it? Well, let's take a look. Looks like we're increasing by 2, we're increasing by 2, we're increasing by 2. So we'd say that to find any term, you got to take this previous term, this a n minus 1, and then we're going to have to add 2. Okay, so this common difference becomes one of the things we're going to use in our explicit. So our explicit, if we use with term 0, we would say that it's an is equal to our first term. If we went, term 0, if I went back to term 0, I would have been at a negative 10. Okay, so negative 10 and then negative 8. So term 0 would be a negative 10. And then, what do we do after that? We add on 2. So it'd be 2 times n. If we wrote it with term 0, or we could say, excuse me, term 1. If I wrote it with term 1, now it's going to be a negative 8, but then it's going to be plus 2 times an n minus 1. So we're going to take the previous term times 2, or excuse me, the previous number times 2, term number times 2, and then add on a negative 8. So either one of those would work. Okay. So if we can tell whether the sequence is arithmetic, justify your answer. If the sequence is arithmetic, then we got to write the recursive and explicit. So a few different things here. So first of all, is it arithmetic? Which means does it have a common difference? So let's look at this first one. Here we decrease by 6. Here we decrease by 6. Here we decrease by 6. So we decrease by 6 each time, so we have a common difference of a minus 6. So is it arithmetic? We'd say yes, because there's a common difference of a negative 6. And then we got to write a recursive and an explicit. Recursive first. So we'd say arithmetic because it has a common difference. Okay. Recursive formula. First term is 22. Any term after that can be found by taking your previous term and minusing 6. Okay, so that's your recursive. The explicit. The explicit one would be this, 2 different ways. You could say that an is equal to, if we went back to term 0 would be a 28. So if we said it would be 28, and then we're going to have to minus 6n. Okay, that would be one way. Or if you use term 1, it would be 22 minus 6 times the previous number. Okay, let's take a look at this next one. Next one, we have a sequence that goes 6, 12, 24, 48. Do we have a common difference? Here we increase by 6, here we increase by 12, here we increase by 24. So no, we do not have a common difference. So we'd say it's not arithmetic. No common difference. Okay. So if I asked you to find the fourth, sixth, or excuse me, 13th term of the sequence that's described, how would I do that? Well, fourth, sixth, and 13th, those are simply the numbers you're going to plug in. So very much like function notation that we've worked with, the fourth term is equal to 6 plus 4 minus 1 times negative 2. So all we have to do is work through this. So I'd have a 3 times negative 2, which gives us a negative 6. So I'd have 6 plus a negative 6, which tells us the fourth term is 0. Okay, if I wanted to find the sixth term, maybe do a little bit more of this without writing it out. Okay, our sixth term, simply replace the n with a 6 from here. Okay, so what do I get here? I got a 5 times negative 2, so that's negative 10. So I got 6 plus negative 10, which gives us a negative 4. Okay, and then the next one, the 13th term, you plug in a 13 for the n, so you'd have 6 plus a 13 minus a 1 times a negative 2. So that's a 12 times a negative 2, which is negative 24. 6 plus negative 24, which tells me that our 13th term of this sequence would be a negative 18. So here are the terms that we're looking for. Term 13 is a negative 18. Term 6 is a negative 4. Term 4 is a 0. Okay, so I will let you try on number 16 here, and then I'll give you the values that you should have had. Okay, so for the fourth term here, you should have had a 27. For the sixth term, you should have had 37. Let me check that one. Let me think through this here. Yes, okay. And then the 13th term, you should have a 72. So hopefully this makes sense to you. If not, you know what you should do. Make sure you come in with some questions. Okay, and today I'll give a shout out to period 2. And that, my friends, is a wrap.